So I'm happy to present you some brief review of Vircator research made in Belarus during, I think, 7 years. You can see in here only small part of our team who participated in this research. And I can tell you that the team is much larger, but I cannot put every name in here. I also will not share with you some publications because there are a lot of them. You can find them all by our names. I mean, via ResearchGate or some other sources. So this research was made in Institute for Nuclear Problems in Belarusian State University. And I will give you a very, very brief review of this long-term research because, you know, several slides shown in one will include the results of research made during several years. So, so when people start working with Vircator, normally they trying to create an HPM source which have some advantages, some well-known advantages. First of all, everybody thinks about compact design. In terms of radiation wavelengths, this type of radiation sources definitely smaller than others one. Another, I think, benefit is low impedance of the source. So you can create high beam current. And when you create high beam current at the same voltage, you can feed your system with higher power. So even with low efficiency, which is disadvantage of this system, you can obtain some high output from the source. Definitely absence of guiding magnetic field is a benefit system, just one subsystem less. And another idea which forced a lot of people start working with Vircators is a very rich physics under this subject. But as I have already told, low efficiency is a disadvantage of the system. And one more phase of this disadvantage is instability of generation frequency. So the idea is to overcome these problems. And the primary objective of our research was increasing efficiency, definitely, and stabilization of operation frequency. From general ideas, it is absolutely clear that certain resonance conditions could solve all the problems. So the idea is to create some type of resonance in this system, and the cavity resonance, creation cavity where some resonance effects present, is a good solution also. And we hope that everybody hopes that putting this type of resonance will also solve another problem. I mean the frequency shifting and mode competition. So the input data, definitely, we started from some type of simulation, but I will show you both simulation and experimental results made at different times with different types of analysis, but both simulation and experiment will present. So the input data for simulation was selection, what we will start studying. First of all, axial Vircator. Another thing is multicavity resonator with fixed operation frequency between 3 and 4 gigahertz. We were limited with the electron beam energy because we have sought initially to make experiments, and we understand it what is available for us or not. And we put it a goal to receive 5% efficiency at least. So the simulation was made, and the first test for this simulation was taken from the publications provided by our Chinese colleagues. They made an experiment and they provided a lot of information about geometry, energy, results, and so on. So we had the possibility to analyze the experimental results and use them as a test for our simulation program. So we used two codes, two peak codes, XOPIC, which is well known, and a code which was developed within our institute. The main difference and the necessity of developing our own code was the feature of XOPIC, which provides electron beam injection into resonator from the anode plane. And we were interested in processes which happened between cathode and anode, how the electron beam is formed, and what happens because of this within the cavity. So we made our own code, and we used the preliminary geometry definition, which is shown in here. So you can see the electron beam passes from your left. There is the first resonator, which length is defined. There are two another resonating cavities, and the output section, the last three serves for matching impedance to the output, to the free space. So that, I mean, zero estimation starting the simulation was selection of the dimensions of the first cavity, which was defined to be resonant for TM011 mode for a cylindrical resonator. All the others are initially defined as having the half of the length of the first one. And we expected that effective matching will provide us with high efficiency. So we expected 5 to 6%, but in simulation we obtained even more. Okay, three variants of geometry were developed and were tested. Three of them were tested numerically, and two of them were tested experimentally. I will show you the results a little bit later. So all the parameters of the resonators used for analysis are shown in here. And some simulation results, which I expect show you the variety of possibilities in here. So first of all, we tested different resonators. I do not show you all the results because there are plenty of them. So just for demonstration. So the efficiency received are even higher than 10%. So this is very, I mean, extremely optimistic, but in any case, we obtained a frequency in the range we would like to obtain. We obtained high peak powers. We tested what type of cathode anode gaps we need to test experimentally. We analyzed different cathodes, and I would like to mention that we analyzed cathodes with a solid surface and with the ring type surface. In here you see I think the utmost result obtained during simulation. This was obtained for the resonator number 2 for the ring type cathode, and in here we expected to observe higher than 15% of efficiency. So let us see what was available in experiment. Again, some results of simulation. You can see that not only the numbers differs, not only the numbers are different for different simulation variants, but also the configuration and face portraits are different. So you can see in here and in here in the matching sections, you receive different figures, and even the momentum values are different for different configurations, even within the same resonator. I can show you this is the same resonator, but different type of cathodes. So after analyzing what we have obtained in simulation, we choose two variants of geometry for testing, and we start preparing the experimental setup for making these experiments, and further discussion will be for the experiment we carried. So we used to supply the Vircator from the huge capacitor bank with the inductive storage and exploding wire array. This was made because of less of limiting ideas for the current to provide to the Vircator. So we were able to obtain 400 kilovolts supply to vacuum diode when the about 600 kilovolt pulse was produced by the exploding wire array. We put it several probes in the system to record the parameters during its operation and to understand what happens inside. All probes were inductive, I mean Rogowski coils placed in different positions of the circuit. I'm sorry, is it okay with connection? I'm receiving some indications of poor internet.
It's okay, but there's some lag in the voice. So maybe you can try turn off the video. Maybe that'll improve things. Let's give it a try.
Yeah, yes, probably it's better to do like this. I'm not sure I can stop. Okay. So let me proceed. So 3 Rogowski coils placed in different places to record what we can understand about system operation. Sorry. So another part of system, this is exploding wire array. It consisted of series of parallel connected copper wires, a lot of them. They had 100 micrometer diameter, and we can vary the length and the number of wires within this array to provide different shape and different amplitude of high voltage pulse. So this exploding wire array was connected from this side to the vacuum vessel where the Vircator parts were placed inside. So in here there is a spark gap which sharpens the high voltage pulse produced from exploding wire array. So the parameters were recorded like having about 400 kilovolts amplitude and about 100, less than 100 nanoseconds rise time. So in here you can see a cathode, and this part is the resonator we have designed according to the simulation we made. So this is a system real view. So exploding wire array, isolator, feeds through, and everything else is inside visible. So multicavity resonator was manufactured according to the dimensions we received from simulation. So in here there is anode plane, so an anode mesh is placed in here. Probably you can see it inside, but I'm not sure it's well visible. Definitely, it was a special procedure to provide proper surface finish and electric contact of elements. You see, there are different spots. It's assembled resonator. So we made special measures to provide perfect electric contact between elements. Because you know this, and even contact of this resonator with the casing of vacuum vessel are important for radiation efficiency. So we paid special attention for this. So another view of this resonator, this is our outside view. In here there is a cathode and different types of cathodes we used. They all were made of graphite. And you can see in here solid cathodes and ring type cathodes. Also, we tested different types of anode mesh with different geometric transparency, and it was fixed on one face of the resonator. So what we were able to observe during the experiments, so this is typical set of signals. Red one is the calculated voltage supplied to the cathode. These two are the currents measured at different places of the circuit, and the blue band shows you whereas the time gap where the HPM signal was observed, it is not shown in here. So how these numbers were obtained? Now you see this is the real setup. These two Rogowski coils recorded, this is the place for them, recorded the current derivative in this part of the circuit. This one is inside the vacuum vessel to record the current close to the cathode. And this value was obtained knowing all the inductances in the circuit and considering what should appear in here. So this voltage is not measured. I can tell you that the diode current measured by this probe correlated well with that obtained in simulation. And what is important for this curve, the first peak on it corresponds to the closing spark gap inside the vacuum vessel, and another one corresponds to the maximum voltage over the diode. So what we observe from the HPM, I mean how we recorded it. So tidal form was detected at large distance from the horn output window by two receiving antennas and recorded by two oscilloscopes, different oscilloscopes with proper bandwidths. So this is a typical time domain waveform and spectral content which was obtained by the short time Fourier from this. Some examples of results obtained for different resonators. So you can see in here indication of there were different cathodes and different cathode anode gaps. And you can see that sometimes we receive single mode, single frequency operation, and sometimes the system changed frequency during producing radiation pulse. So what we did, we selected the experiments with the highest output power, and also we paid attention to keeping the same frequency during system operation. So another example of the result, this is the, I mean the best obtained result from these experiments. You can see the single frequency operation, high amplitude, and in here you can see the difference in between the experimentally obtained numbers for this best high power generation from this Vircator made with multicavity resonator, and what was proposed by simulation. You can see the frequency is correct, but different types of cathodes promised better results. And also the cathode anode gap are different. This can be easily explained because you understand well that when we are working with explosive emission cathode, we have the plasma expansion from the cathode, and the cathode anode gap changes because of this plasma expansion, which was not definitely included into consideration, I mean, in simulation. This effect was not included. So in simulation, we put the gap value from which the emission, I mean radiation starts, and the some time gap is needed for creating the emission cloud, the electron emitting cloud near the cathode. So this is the reflection of this time gap, which is necessary for this explosive emission process. Another variant is with Resonator 2, and again we see that we have already received close results. Frequency is close. Parameters are again very close, but again the better result was received not for the cathode which was promising the better result for this resonator, but in any case all the numbers are very close. So if summarize the experimental results, we can tell that first of all, multi-cavity resonators work. And if we put this system, this component into Vircator, we can expect increase in their efficiency. Also, we can expect some stabilization of frequency, but the experiments are poorly reproducible. So we can put the same values to the system and record different HPM signals from them. Definitely, we understand that preliminary simulation we made was quite idealized, and the parameters of the electron beam, which was injected into resonator, were considered to be set definitely, and beam was assumed to be homogeneous. I mean, distribution of current within the beam cross section. This beam was assumed to be monochromatic. So additional analysis definitely is required to understand what happens inside the system. And we did this additional analysis. So it was decided, first of all, that we need to consider all the phenomena conditioned by the explosive emission. We need to consider what happens if we understand that the electron beam cross section do not coincide with the median surface cross section. We need to understand what happens when impedance of the system changes. We also need to understand what happens when we add some energy spread to the beam, which is practical for the system. So we have analyzed what are the ranges for the parameters to test, and they were also involved into simulation, which was made by XOPIC again. This is a simple model. Again, we have some cavity, some fast cavity, and other parts which are described, some parameters and some fixed frequency which we want to observe in our experiments. So what we received? First of all, we obtained that there is the optimal diameter of the beam. Probably we need to speak about not the optimal diameter, I mean the diameter which produces the highest efficiency. Probably we need to speak to about the optimal current density over the cathode. But in here it is analyzed as beam diameter. So you can see some numbers in here. Oh, sorry, I see the mistake in here. There are numbers for radius, not for beam diameter. Beam diameters are indicated in the lower line. And we can see that this optimal number should be, exactly fitted, because even changing in beam diameter, 10% decrease in beam diameter leads to drop of the radiation efficiency immediately. Another thing which is very much important, this is beam impedance, and again we can speak about the optimal impedance value, and you can see that this optimal impedance value gives both the higher efficiency and the single frequency operation, because in here you can see a lot of frequencies, and in here for the optimal impedance zone, you can see that we receive the single frequency operation. And this value for our parameters was obtained between 30 and 35 ohms for all types of Vircators. Another factor which was analyzed is beam energy spread. And you also can see that increasing of beam energy spread is absolutely fatal for the efficiency of system operation. So we need to keep it small, but nobody knows how to do this. And again, when we can keep it small, we receive single frequency operation. And when we increase the spread, we will receive additional frequencies into the output of the system. So what to do with this knowledge? The question about the energy spread was answered in also long time research when we studied why ring type cathode provided better results, provided highest output for this type of experiments. And during this research, we have observed that there is a new effect in here, a new effect which results in electron beam accumulation, which is made without magnetic field inside the vacuum diode. In the center part, we can produce very, very high dense thin electron beam in here. But additional result from this research, additional feature, such type of beam has lower energy spread as compared to a solid cathode. And this can explain why we have received higher output in the experiments with ring type cathode. And you can see on my previous slides that the highest output power we received from this system was received when we used the cathode with the ring type shape. This is very, very interesting results. And again, this is one slide showing the 3 years theoretical and experimental activities shown only in one slide. So, where to move forward, seeking for efficiency control. We do understand that multi-cavity resonators work, and they work perfectly. And the only thing we now can analyze is the diode properties and the electron beam properties, which can be changed by changing two elements, two components participating in producing electron beam in our system. I mean cathode and anode, because we even have no magnetic field to change it for producing different beam properties. So in here, in such type of system, what is important, first of all, we must consider to increase rise time of the current pulse, which we are producing, which is determined definitely by exposition conditions on the cathode. Definitely it depends on what we supply to the system, but even when we are supplying the same pulse, different shapes, different materials, different conditions created on the cathode surface for starting electron emissions can be very important for this parameter. Another thing is current density distribution. So we need to consider that beam should be uniform. I mean, current distribution over the cross section must be uniform. And again, energy spread is a thing which is very, very important for the system operation, as we see. So we need to see about these subjects when considering Vircators and all the systems of this type. And one more thing which must be considered is reproducibility of parameters, because it's very difficult to control when you have several, I mean, discharge gap inside the system, you have some instability of operation of a power supply, and you have some freedom in operation of cathode, which is which works due to explosive emission. So you must try to fix these parameters of the system to provide high reproducibility of system parameters. So what is the conclusion, the complete conclusion to this presentation? First of all, as we showed in our research, increasing the efficiency and stabilization of operation frequency, which were declared as the objectives for this research, can be done. So resonant conditions provided by the multicavity resonator is good for both increasing the frequency and stabilization of increasing the efficiency and stabilization of the operation frequency. We need to take care about explosive emission conditions, about vacuum diode properties, and so on. And to win in this game, we need to understand deeply all the physics which is inside the phenomena. And only in this case, we will take the most from the nature. And the final citation I would like to show you, this is a citation of a very well-known book. You know, we are working in science, but normally this is very close to the art. Our science is very, very close to the art. So thank you very much for your attention, and I'm open for your questions. So in addition to the cathode and gap resonance, we also have a plasma frequency resonance. Is it possible to make them equal and get more power output and thus increase efficiency? Normally, this is an idea which everybody tries to follow, to match these two resonances in one. And this is great art to achieve this. We tried to put them together, and you know, this is play with nature. When we're trying to take more from it, it requires more from us. So this idea requires a lot of efforts to achieve. It is possible. It is possible at least to put them. You know, you have some bandwidths to determine all these frequencies. So to put them into the same bandwidths. But this is an art, actually. Thank you, Professor, for asking this. I like this question, and I do understand how much we need to do to achieve this. Again, from Professor Gini, in your actual Vircator, you seem to be radiating from a horn. Yes. Yes, a horn TM01 mode, which have null on the axis. Don't you need a mode converter before the antenna? We thought about this, but this research was not made for providing the source for some application. This was made for research. Definitely we thought about this, but this added additional element into the design and additional element to be controlled. So we prefer at that stage, we prefer to use horn without mode converter, but we thought about this. Again, thank you for this question.
I think the next three questions are more or less about efficiency, the next three questions.
Yes, how do you calculate efficiency? This is simple estimation. We recorded current and voltage at the cathode, so we can calculate the input power, put it to the, put to the beam, and from measurement of electric field, we can calculate the output power, and this divided give us efficiency. So this is the calculation of efficiency we used both for simulation and for measurements to put them on the same flow. Okay, again, question of Professor Giri. We have electrons with no DC magnetic field and efficiency for 40%. Isn't your goal of 5% too small? This generally this goal is too small. It was interesting to make a Vircator with this efficiency, which is actually high for Vircators. Definitely, if compare Vircator with other sources, they are not so good probably, but it was interesting at that time. Actually, yeah, Reltron have high efficiency, definitely. Okay, I see some question from Ernesto. Thank you. What definition of efficiency, what used in this study, I have already answered. We calculated, yes, peak power, output, peak power, input, yes. Definitely this type of efficiency. What power do you use for calculation efficiency? Peak power, not average.
Okay.
This is a question from the Dr. Andreev.
Dr. Andreev.
Yes.
Thank you so much. If I can ask you a quick question,
Yep.
what did you use to generate the voltage? What voltage levels were you inputting to the device? And what did you use?
I can show you.
Was it the Marx generator?
No, it is not Marx generator. This is a special setup. I'll try to show again my presentation. I'm not sure you can see. This is a specific setup. Those who work with inductive, so you can see probably on schematics it's better. We have a capacitor bank, a discharge gap, which closes this. We can start putting voltage from this capacitor bank to the circuit. In here we have inductive storage, and we have exploding wire array. If you do remember yesterday's report made by John, they tested the conductive fabric for lightning protection.
Yeah.
Yes, and there they considered the effect of high current passing through these conducting wires. This is the same. We are putting high current into conducting wires. Their resistivity grows, and when their resistivity grows, the voltage in between these two ends starts increasing. And the increasing of this voltage can be very high. So we can produce, if you have in here 100 volts, during explosions of an explosive wire array, we can produce 1 megavolt. And this high voltage is high, but the pulse is short. This high voltage pulse can be applied to the electron beam accelerator to produce electron beam.
Very interesting. Thank you so much again, Doctor. Thank you for the nice presentation. Thank you.
Thank you.
Much appreciated.
Thank you.
Thank you.